So in round number two, you have a second classifier, which is now incorrectly predicting these ones. And over here, then these ones are given a higher weightage in the next round. Round number three, these ones are given a higher weightage, and so on and so forth. And so over here, after three rounds, you've built three different classifiers. And these are all, like I said, a single rule, right? So it's just a single rule which is dividing, which is saying maybe, x less than 5, and over here, x less than 10, and over here, y less than 3, or something like that. So very simple classifiers. The combination of them, it ends up with this very nice classifier over here, which in the end is able to make a very high quality prediction. And so you're able to get a final model which is very low bias, and it has high training accuracy as well. And usually this is a model which also generalizes well and does well on the test data set as well. So now let's get on to a different way of doing the boosting procedure. And we'll talk about gradient boosting, which is an extension of the ADA boost algorithm, in a way which might not seem very straightforward, because it uses gradient descent in a space of functions rather than doing it in a space of data as you're normally associated with in linear regression and logistic regression. So before we get into the details of it, let's suppose we want to know. Let's suppose you want to play a very quick game, right? You're given the data set, S is equal to x1 y1 x2 y2 up till xm ym. So you have m data points. Your input x is some vector, and your output y are dual valued. So this is a regression problem. Your task is to fit a model to minimize the square loss. Remember, the square loss is the model prediction minus the actual, the sum of the square of that, the sum of that over all data points. That is your squared loss, right? Now, to solve this problem, suppose your friend wants to help and they give you a starting model F. You see the model's outputs and you see that it is good. It has a low square loss, but it's not perfect. So, how do you actually improve this model, right? You're not allowed to change the model your friend gave you at all. But you can add a new model G to the output, such that you are, instead of predicting f of x, so predicting f of x plus g of x as your final regression output. So what do you do in such case, right? This is your final. So your question now is, how do you find this value g, this function g, which you're able to sort of correct the outputs given by your friend's model. So what do you do? How do you like find? How would you create G? What would be the criteria you're going to use for creating G? So if you look at the example over here, this is what we want. In the ideal case, we want G of x1 to be exactly, y1 minus f of x1, right? You want exactly the error in your friend's model to be predicted correctly by G, and then your G of x plus f of x will give you the correct answer. So that's exactly what you have to do. You have to train a model using the input x1, x2, x3, etc., and the outputs as y minus f of x1, what's called the residual. So you have to train a model, a simple regression model, on the residual of the model before it, right? And this gives you a better model. When you do f of x, when you do f of x plus g of x as your final output, that is actually going to be better than just having f of x. And the great thing about this is that you can create a model on top of this, right? You can create not just G, but you can create G1, G2, G3, which is taking the outputs of the models so far, and it's the residuals of that it's taking, and it is learning to predict that. It's learning to predict basically how to course correct the model outputs for any given input. So this is the idea behind gradient boosting. You continuously keep on doing this, and you keep on training models on the residuals. This is really the essential idea. It's not much more complicated than this, but requires a little bit of thought into why this actually works. So, so now let's discuss how this, how this works and why it's related to gradient descent and why the gradient part comes in this boosting procedure. So, like we said, we had the loss function, which is just over here, the squared loss, right? You're dividing it by 2, and this is a very okay thing to do. You can always scale your losses by any value. It won't change the model you're obtaining. So now we want to minimize this, and we want to do this by adjusting f of x1, x2, and xn, right? Now, these are just some numbers. These values, these outputs of the model, f is just some numbers. So you can treat them as parameters, and you can basically calculate the derivative with respect to this derivative of this loss. The loss over here is, your simple loss function, your squared loss, right? So what is the derivative of j, which is your total squared loss, with respect to each of your data points, right? Your each of the outputs of your function f, rather the predictions of your function f. If you calculate that and you work it out over here, it turns out it's actually the residual. So the gradient over here is actually just your residual, right? Just your prediction minus your true value y1. And this is a very interesting property because this means that as you're adding more models, you're actually doing a sort of gradient descent in the space of the predicted values f of x1, right? And so you can interpret these, you can use each of these as being a negative gradient. And so what happens is that instead of having your predictions, instead of having weights as you normally do with linear regression, you have a uh, a vector of your residuals, right? Which is your predicted, y1 y minus f of x1. That vector becomes your sort of weights. And so with gradient descent, as you add one more model, that is basically equivalent to taking a step, you change your residuals which you're obtaining from the combined model f of g, f of x1 plus g of x1, uh, sorry, my bad, f of x plus g of g1 of x, plus g2 of x plus g3 of x. As you add more and more models that way, you are essentially changing the residuals, and you're doing gradient descent to update the residuals as if they were weights. And the reason for this is because for squared loss, the derivative is actually just a residual. The gradient is just a residual. So as you see over here, very similar to how you have your thetas, your weights, you're basically just doing a gradient descent on the residuals itself, right? So this is a very interesting way in which boosting using this simple rule is actually related to gradient descent. And this is, there's something called functional gradient descent, which is basically what is happening over here. You can go and look up functional gradient descent to really understand some of the mathematical concepts. So gradient boosting is a very powerful procedure. It's used a lot in very popular tools like LightGBM and XGBoost. So it is something that is very practical as well, in addition to AdaBoost. And so, in general, this is the overall procedure. As you see, you initialize it, just by using some. You can initialize the initial model to be whatever. This is, remember, the model given to you by your friend. So it doesn't have to be a very good model. You can just use, for example, for every input x, it just predicts the mean value of all the targets. If you just take the average value, it'll just predict that. So it's just a simple, heuristic rule also will work. And then iteratively, you are computing this residual RIM for each of the I examples. M is the number of rounds over here. So for each of those, you're calculating the residual value of the gradient. The residual value is the gradient, sorry. And you're fitting a regression tree such that you are actually predicting the residuals. You're trying to predict the y minus f of x. You're trying to predict that value. You're trying to predict basically the error made by the model so far, right? That is what you're trying to predict. And then you, of course, add them together. Sorry. You add them together to get your final model, uh, and you iteratively do this. So you create f of f0 of x plus f1 of x plus f2 of x, so on and so forth, up to fmx. So you'll create this sum of f of m models to be your final model, right? And then you use that as your regression output. And so the idea is basically that, the first model is sort of wrong. The second model is trained on the errors of that. The third model is trained on the errors of the first two models combined. The fourth model is trained on the errors of the first three models combined, so on and so forth. So you are slowly narrowing and reducing the total error which is made by the total combined model. And this gives you a final model which is very low bias, and also it's a very good predictor. Uh, this works for regression. For classification, you have to do a few modifications to this algorithm to get to work. So finally, just to sum up on gradient boosting, it's boosting plus gradient descent. It's boosting because you're iteratively trying to reduce the errors of the models previous, and you're creating new and new models as you're doing it. And the other key of boosting is that each model itself does not need to be a very powerful learner. It doesn't need to be something like a neural network. It can be a very simple decision tree, or even a decision tree with just one rule, which is called a decision stump. And over a number of rounds, you're iteratively using that simple learning algorithm to create a better and better classifier, or a better and better regression model, right? So in each round, you introduce a weak learner to compensate for the shortcomings of the existing weak learners. Now, the difference between AdaBoost and gradient boosting is that in AdaBoost, the shortcomings are identified by your high-weighted data points. The vector where the probability scores were high, that is how you identified which data points to focus on. Over here, the shortcomings are identified by the gradients, the residual, boosting procedure. Okay, that should be it from my side. Thank you so much for listening to me, and I hope you enjoy the rest of the series.